Okay. Hello, everyone. Today, for a discussion section, we're going to be covering evaluation metrics, specifically for classifiers. So for a quick overview of the different topics that we're going to cover, first we're going to be going over the motivation behind evaluation metrics, why we need these things. Then we're going to sort of dig in a little bit into the binary classifiers and get a bit of an intuition as to what the rank view of those things might be and various concepts of thresholding. Then we'll cover some specific metrics, starting with the confusion matrix and then deriving various point metrics from the confusion matrix, as well as some threshold-independent metrics, also known as summary metrics, including AUROC, AUPRC, and log loss. And then finally, we're going to talk a little bit about how these metrics transform under various cases, such as class imbalance, and see how these various metrics fail in those cases. And then as well, we're going to look into some multi-class cases. Okay, so let's get started. Let's start with the motivation. So at a very high level, we have this training objective that we're typically optimizing over. And that training objective is typically, we want it to be differentiable. And for that reason, it oftentimes is only an approximation for the true metric that we really want to optimize over, or the real world objective we care about. Ideally, you'd have the training metric be that objective, but for many cases, that is not possible. We saw on Monday, for example, that for decision trees, misclassification loss, which is one of the losses that would be a real-world objective, is not sensitive enough to pick discriminative splits, so we end up optimizing over cross-entropy loss instead, for example. And having these metrics generally helps organize your ML team as a whole towards specific goals. It sort of gives you a measure of the progress that you're making. And you can do so by looking at the gap between your metrics in different cases. So for example, you can look at the difference between your gap between your desired performance and your baseline, which tells you how much effort you think you would need to put in. And it gives you like an estimate of how much effort that would be. You also have your desired performance versus your current performance. So that tells you sort of an estimate of how much more effort that you would need to put in. And then it also lets you measure your progress over time. And generally how this kind of thing is done is that you evaluate it on a development or validation set. And so you're evaluating your progress on this metric over this validation set. And then once you are done optimizing the validation metric, you then evaluate once your test set metric. It's also fairly useful for debugging, and that's something that shouldn't be taken lightly. Typically, when you first build an ML model, it will not work, probably the first couple times. I've never had something work the first time I built it. And so starting with very simple models and using these metrics as a sort of sanity check of sorts has been very helpful. It is something that you will definitely do. It also helps you diagnose various bias versus variance issues. You can imagine training multiple models on different subsets of the data, for example, to get an idea of the variance of your models. Okay, so that gives you a little bit of a motivation. The motivation. Are there any questions so far on that? Actually, let me go back. Yep. No, that door can be closed. If someone wants to close it, they can go ahead and do that. But thank you. Good question. The question was, why is that door open? Okay. Okay, let's talk about binary classifiers. Okay, so you guys are probably all fairly familiar with this, but really for binary classification, you have your input X, right? That's your data. And you have a label Y that you're trying to predict, right? In this case, for binary classification, you have either a 0 or a 1. And then you have your model, which is predicting y hat, which is really just, it's learning some function that it's applying to x and predicting that y hat. Okay, fairly standard stuff so far. What gets a little bit interesting is you can sort of divide up the models that we've looked at so far into a couple different classes. The first one are models that output sort of a class directly. It sort of like tells you directly what kind of class you're looking at. And examples of that are like k-nearest neighbors or decision trees, where basically you just take the most common element you see in whatever return set you have and predict that as your most common class. However, for some other models, like SVMs or logistic regressions, you instead are outputting a real valued score. And so for example, for SVMs, that's oftentimes a margin, so how far away you are from the margin sort of determines how confident you are in the score one way or another. And then, on the other hand, logistic regression and neural networks to a certain extent predict it as a probability instead, or a probability of the example being a positive or negative. And so for any of these score-based classifiers, since our end result is really a binary classification, we want to make sure that we set a threshold, essentially, because we can say anything above this threshold of probability we can call a positive example. Anything below this threshold we call a negative example. And it's sort of like you really do need to pick a threshold in order to make that classification. And because this is sort of the harder type to look at and talk about metrics in terms of, we'll sort of focus in on this second type. Okay, so talking about score-based models first, a little bit of sort of background or terminology here. So you have here the outputs of some predicted model. Say you have a model that is predicting these scores, okay? And you have the true positive examples labeled in green, and the true negatives, or the examples actually labeled as a negative, labeled in gray. And when your model outputs scores, it'll output a score between 0 and 1, and the various points will fall somewhere along this scale. You'll also have this notion of prevalence, which is sort of the ratio of positives to the total number of examples you have. So in a class-balanced problem, you'll have a prevalence of 0.5 since you have an equal number of positives and negatives. And so one thing to note here is that at a certain level, for ranking purposes, the actual absolute score doesn't really matter. What really matters in this case is just the relative ordering of the different elements. And so if you shifted this green example slightly up, the overall ranking would still be the same. And we're going to see that for many of the metrics we're going to look at, that absolute position doesn't matter so much. And it all depends just on the relative ordering. Another thing to note is that if you have many more more examples in general, it might not become feasible to really plot it out in this format. So oftentimes people will look at histograms instead to look at the class outputs, or the predicted outputs. One final thing to note before we move on from this kind of view is that for this rank view, it's actually very useful from an error analysis perspective, where if you want to sort of look at what examples you got wrong, it's oftentimes useful to start from the top and hit your first negative examples, and those are sort of like the examples that you got the most wrong. And it's useful to start from those to gain a really good insight into how your model is making mistakes. And on the flip side, you can also start from the bottom and start with your first positives you hit there to get an idea of why your positives are being misclassified. Okay, so I was talking about setting a threshold for this classification problem, right? You have to basically pick a threshold. Let's, in this case, just arbitrarily pick the threshold of 0.5, okay? And once you pick a threshold, you sort of just automatically divide up your space into these 4 different categories here. And also, once you pick a threshold, you've changed your score-based model into a classifier. And so this threshold sort of gives rise to, this threshold sort of gives rise to this overall sort of matrix-like format here. And that's what we're going to be getting into right now. So that's sort of bringing us to this confusion matrix. Okay, so when you divide up, you pick this threshold, you get these 4 different categories, right? You have this column here, which is your examples that your model has predicted as positive, which you can then split up further into the ones that are actually positive, these are the ones that are actually positive, and they're divided into the examples that are predicted as positive versus predicted as negative, and then the right column is instead the ones that are actually negative, and again divided up into those that you predict as positive or negative. And some things to note just right off the bat is that the total sum of points in each of these things is fixed, right? Because you have a fixed number of examples, and they're going to have to fall into one and only one of these categories. Another thing to note is that sort of the sum within each column is also fixed, right? Since you have a fixed number of positives and a fixed number of negatives. And then finally, for the rows, that is actually more determined by the quality of the model and the selected threshold. So if your model is very good at sort of picking out the positive versus the negatives, you'll expect more weight on the diagonal and less weight on the off-diagonal, because this diagonal is sort of the correct examples that you've classified, and the off-diagonal is when you've labeled it differently from what the true predicted value might be. So now let's just come up with a little bit more terminology to describe the specific elements of this confusion matrix. So I briefly described it before, but this top left quadrant right here is oftentimes referred to as your true positives, as in it is the examples that are labeled as positive that you also predicted as positive, so you got them correct. Okay? Your models predicted them as positive, and they are positive, so they're true positives. Down here, sort of the flip side, you have the ones that are actually negatives that your model has also predicted as negatives. Those are called true negatives. And these are sort of like, again, the true positives and true negatives are your good examples, the ones you've gotten correct. And then looking at the off-diagonal terms, we have false positives. So it's the ones that you predicted as positive, but were in fact negative, so you falsely called them positives. And then finally, we have the false negatives, the ones you falsely called negatives. Okay, so we have true positives, false negatives, and true negatives, and many of the point metrics that we deal with can be expressed as sort of combinations of these different terms, which is why it's pretty important to get a good feeling for what they actually mean. One other definition of false positives and false negatives you might hear, which there's this graphic here, which came from somewhere on the internet, I'm not sure where, but you will oftentimes hear them called type 1 versus type 2 errors, where type 1 are your false positives and types 2 are your false negatives. Generally, your training examples are going to be a little bit harder than this, but it's just a funny graphic to keep that in mind. Okay, so I've talked about point metrics for a while. We've derived these true positive, false positive, etc. Let's talk about some actual metrics. The first one we talk about is accuracy. Okay? And at a very high level, accuracy, you can think of it as just the proportion of examples that you got correct. Right? So you just take the diagonal, the true positives and true negatives, and divide it by the total sum of examples that you have. So basically, they're just the sum of the four quadrants. And when you're improving accuracy, you're basically optimizing a 0-1 loss function. So if you were able to write out a 0-1 loss function and sort of optimize over that directly, you'd effectively directly be optimizing your accuracy. So 0-1 loss in the binary classification case is it's basically misclassification loss. If you recall from a couple lectures ago, it's if an example is correct, right? If it's actually positive, your loss will be 0 if you predict it positive, and 1 if you predict it negative, and then vice versa. So it's basically just you can sort of imagine it as like a stepwise thing, where it's just like if you got it right, you get full marks, and if you get it wrong, you just get no marks, right? And you can imagine that kind of loss is actually kind of difficult to optimize because it's sort of very abrupt, right? It's either you get it right or not, and there's no real gradient. And to be clear, the question was, can you clarify what 0-1 loss is? Should probably do it in another order next time. Okay, any other questions? Yep.
Earlier, the title said confusion matrix.
Yep. The question is, okay, why do we call this a confusion matrix? Okay, it is a little bit of a confusing topic, but really, the reason why we call it confusion matrix is because it gives you a high-level overview of how your model got confused, basically. Right? So it's like if your model, like these false negatives and false positives, you could see as incorrect classifications, and basically as confusion of your model. And what's interesting is I'm going to get into this a little bit later, but you can also generalize this to like multi-class cases where you have much larger matrices, right? And then you can sort of get a much better idea of like which classes are being confused as which other classes. So you can imagine like an object classification problem, right? Where it's like maybe you confuse dogs for cats or something like that. Any other questions? Okay. The next point metric we can talk about, this one is the first of the ones we're going to look at that don't factor in all the values, is called precision. Okay? And that's just the true positives divided by the true positives plus false positives. And the way to think about this one is it's basically of all the positive predictions you're making, of all the values in this top row here, how many of them are actually correct? Like how pure are the positive predictions you're making? This is also called the positive predictive value. And something like this is very useful for a ranking problem, for example. We're going to get into class imbalance later, but if you have a lot of negatives, right, you don't care so much about your negative classifications. What you care about is sort of those top predictions and if they're good or not. So if you're Google and proposing some top search results, you want those top results to be good examples. Okay. Another metric that you can look at is recall, or it's sometimes called positive recall or sensitivity. And this one, we're still factoring in the true positives, but now we're dividing by the true positives plus the false negatives. And the way to think about this one is that it's really, you're looking at your overall space of positives and seeing how many of them you have successfully classified as positive, right? And so this is actually like a terminology that's borrowed from lab tests, for example. So you could imagine where your positives are like diseased people. Your recall is how many of the diseased people did you successfully tell were diseased, right? And this, you can sort of note that that recall versus precision are somewhat related to each other. They both have this true positive term here. And so there's a bit of an interaction between these two, and we're going to get into that shortly. A couple things to note about precision and recall. It's kind of trivially easy to get 100% recall or 100% precision. For recall, if you just classify everything as positive, then sort of trivially you will get all the positives correct. So like if you move the threshold all the way down here, your true positives, your false negatives would go to 0 and your true positives would go to, well, the ratio of true positives to false negatives would go to 1. And on the flip side, for precision, right, if you predict nothing as positive, then sort of by definition, 100% of your positives that you predicted are correct, right? If you make no predictions, it's very easy to not make any bad predictions. Okay. And so just to be clear, for good precision, basically, you want to, so if you fix like recall, like say you want 100% recall and then you're optimizing over precision, what you want is you want to move the lowest sort of green example as high up as possible, right? If you're fixed at 100% recall, then you're basically required to have your threshold set below the lowest positive example, and then it just becomes a matter of optimizing that lowest positive example. And similarly for good recall, having fixed 100% precision, you sort of want to bring the negatives as far down as possible. Are there any questions about precision or recall at this point? Okay. The next one we'll look at is called negative recall or specificity. So positive recall sort of dealt with the first column. Negative recall deals with the second column. It's true negatives divided by true negatives plus false positives. And you can think of this one as basically the number of all the negatives that you classified correctly as negatives. So just like how positive recall is the number of all positives that you classified correctly as positives, negative recall or specificity is the number of true negatives that you got out of all your negatives. And so, yeah, one thing that is going to be very relevant shortly is negative recall and positive recall deal with separate columns entirely. Okay, so they don't have any of the same factors. Okay, so we've talked about accuracy, we've talked about precision, we've talked about recall. Sometimes people are interested in looking at precision or recall specifically, but they want to come up with one number that sort of factors the two of them together. And people have come up with this F1 score, which is basically the harmonic mean of precision and recall. And so harmonic mean is, just to be very clear, right, harmonic mean is just the sum over all your examples. Well, say you're taking the harmonic mean of xi's, right? It's this is the arithmetic mean that I've written here, right? And then the harmonic mean is you just invert the individual x's and then invert the whole thing. And this works well for rates or ratios, which is something like precision or recall. There's also the geometric mean, which is another score that people use. That one's not up here. People oftentimes call it the G-score. And that one is just the geometric mean. So in that case, it's just the product over all your i's of xi, right? And then to the 1 over n, where n's are the number of examples. Any questions on this? Okay. Yeah, so to be clear, the reason people came up with the F1 and the G-score, for example, are to sort of to use precision and recall, which are both sort of terms that we make a lot of sense to us intuitively, and sort of factor them together into one overall score. So these are all point metrics, what we call them. And the reason we call them point metrics is because they sort of depend on us setting the threshold at one very specific point. And so when you change this threshold, it tends to change your metrics. And so they're very dependent on what that threshold might be. So in this example here, we sort of move the threshold up a bit, and that has caused some examples that were labeled positive that we predicted correctly to now be predicted as negatives instead. And so that sort of badly affects your recall, for example. One thing to note is that really there's only a certain number of effective thresholds. And what I mean by that is, like, if you move the threshold up from 0.6 to 0.601 or something like that, you wouldn't actually change any of these point metrics. They're still making the same overall classification. And though the threshold is technically different, none of your point metrics really change. And so we call it effective threshold because it's really, each effective threshold actually has an effect on your point metrics. And it really turns out that the number of effective thresholds you have is just n plus 1, where n is the number of examples you have. Any questions on thresholds? No? Okay. So one thing that people often ask then is, okay, well, if you can change the threshold, right, all these values sort of depend on what threshold you set. But if you don't want to commit to a threshold right off the bat, what can you do? And one thing people do is they do this thing called threshold scanning. And they basically just pick a bunch of different thresholds. Right? In this case, we've sort of drawn them out as these dotted lines here on the left. And then you can record what each of your metrics will look like according to this threshold scanning. And so basically, each one of these thresholds is giving you a different classification model. Right? Because if you set your thresholds to 0.05, then your classifier is going to return 1 for anything that's above 0.05 and 0 for anything that's below. And when we look at this table on the right, there's a couple interesting things that I think you should note. One of them is that your recall, for example, as your threshold goes down, is monotonically increasing. It only goes up, right? Because as you're bringing your threshold down, you're classifying more and more of your positive examples as positives. And that's what recall is, right? On the flip side, you have your specificity is monotonically decreasing. That's the number of negatives that you correctly classify as negatives. So as you bring this threshold down, you're classifying less and less examples as negatives. And so you're losing out on your specificity. However, something like precision, this column here is a little bit more interesting in that it's not actually monotonically increasing or decreasing. It's generally decreasing because as you factor in more and more negatives, your overall precision, how many of your positive examples are actually positives, is going down. But if you add another positive to your positive predictions, then your precision actually bumps up again. So like, for example, if you're switching from here to here, you're adding a positive and your precision is going up. And then sort of trivially, I guess, you can see that the true positives, true negatives, false positives, and false negatives are all monotonically increasing or decreasing. And one thing that I want you guys to note as well is that your precision versus your precision and specificity, so these two columns here, are sort of having a trade-off with this middle column, or recall here, right? As your precision goes down, your recall goes up, and vice versa. And that sort of trade-off there is something that we're very interested in capturing. So this is sort of, how do we summarize this trade-off of recall or sensitivity, which are the same thing, right? They're just two different terms, versus precision and specificity, which are sort of related concepts, right? And to be clear, I can write out precision. I'll just write this out over here. Precision is just your number of true positives divided by true positives plus false positives, right? Again, this is just repeating what I had up on the board before. It's like how many of your positive predictions are actually correct. Your recall is really just your true positives over true positives plus false negatives. That's how many of your positives you got correct. And then specificity, let's see. Specificity is just your true negatives. I'll just write that up here. It's just your true negatives divided by your true negatives plus. Let's see, which one is this? Of course, I'm blanking now. Okay, true negatives divided by true negatives plus false positives, right? Since it's all your negatives, all the things that are actually labeled negative, and it's how many of those did you actually get correctly. And again, right, this here is the same, right? This is equal to sensitivity. All right, so you can sort of see that your precision or specificity, right, sort of have this trade-off with your recall, right? Where you are, if you can predict more of your examples, like if you get more of the positives, your precision will go down because as you're letting more in, you'll also mix more things together. Okay, so we've talked about this trade-off. One way that people deal with this trade-off is looking at these things called, various curves. And so one curve that people look at is called the receiver operating characteristic curve, or the ROC curve. And what we've done here is we've basically done this threshold scanning. And at each threshold, you can determine what your sensitivity versus specificity might be. And so at each threshold, that gives you 1 point on this graph. So, for example, some threshold, maybe it's like 0.5 or something, will give you a specificity of 0.4 and a sensitivity of 0.9. And so one thing that you should note is that if you were randomly guessing, you would essentially get this dotted line along the diagonal. It's like as you're letting in more, it's basically completely random whether it's good or not. And one summary metric, so this curve already gives you a pretty good visual representation of how well you're doing. One summary metric you can compute that gives you one overall thing that's sort of threshold independent is the area under this curve, or people call it the AU-ROC, the area under the ROC curve. And that really gives you sort of an example of how well these results are ranked. You might see instead a slight variant of this curve where people will plot instead the true positive rate versus the false positive rate. And that effectively just has the effect of rotating this curve 90 degrees. But it's giving you the same impression. And false positive rate is just 1 minus the specificity. So it's really the number of false positives divided by the true negatives plus false positives. So it's how many of your negatives did you get incorrect. Okay. One more thing to note is that there's you can see some jags in this curve, right? There's certain parts where it's going straight for a while and then it turns, right? And what those correspond to is it's when you flip from series of positives to series of negatives, right? So you can imagine as you're bringing the threshold down, if you're only hitting positives, you're increasing your recall and you're keeping your precision the same. Or you're increasing your, you're increasing your sensitivity, right? Because you're getting more and more true positives, and your specificity is staying the same because you're not changing the classification of any negatives, which is what specificity deals with. However, once you start hitting series of negatives, then your specificity starts going down, and your recall or sensitivity stays the same because this only deals with with things that are labeled positives. Does that make sense? Any questions? Okay. And so one intuitive way you can sort of think about what the AU-ROC means, right? I sort of described this curve, and there's this area under the curve. There's actually, it turns out there's a fairly easy way to think about what the AU-ROC means. And really what it means is if you pick a random positive example from this set here, and a random negative example from this set, what is the probability that that positive will outrank that negative? Okay, so it's like you randomly pick a positive, randomly pick a negative. What is the probability that your model will correctly be able to say that which one is higher? And for the longest time, this was something that I sort of just knew, and I didn't really have a reference for it or anything. So just recently, I actually went looking through the literature, and I found this paper from 1982 that was in radiology. And basically, they were just looking at disease versus non-disease patients and defined it all in terms of that. But this paper is like 16,000 citations or something like that because everyone cites it for the AU-ROC term, even though it's kind of funnily specific to only radiology. So I talked about the precision recall curve, the ROC curve, which is specificity versus sensitivity, right? And I said that specificity and precision are sort of related. So one thing you can do is instead of comparing these two terms, you can compare these two terms instead, right? And that gives rise to what we call the precision recall curve instead. And right off the bat, you can notice that there's some kind of things that are different here, right? Sometimes it goes down, and then sometimes it increases again. And you can sort of right away see why that is, because versus where the specificity versus the sensitivity had entirely different terms. They share no terms with each other. The precision versus the recall do share the true positive term. So when you get things correct, that actually positively influences both your precision and your recall. And so you can sort of see that what happens is as you're bringing your threshold down, right, you're increasing your recall, you're increasing your precision, right? But then once you hit a series of negatives, what happens is your recall stays the same. You're not getting any new positives. However, your precision is falling off. So every new negative you hit, your recall stays the same, but your precision goes down. And that's why you have these sharp drops here. Versus when you start hitting positives again, then you start having a positive increase on both your precision and recall. So you have these sharp drops, and then these gradual increases again. And so you can sort of also compute an area under this curve, so the AUPRC. And that gives you this sort of average precision number, which is like if you picked a random threshold, what would your expected precision be? A couple other sort of things to note is that versus the ROC curve that we were looking at before, right, just to go back to that for a second, sort of starts in one corner, ends in the other corner. The precision recall curve does not do that, right? All the way at the right here, it ends about midway. And the point it actually ends at is the prevalence, or the ratio of positives to negatives you have. And that's what it makes sense, because if you set your threshold down to here, your recall is 100%, but your precision isn't 0. You're still getting whatever ratio of positives to negatives you have right. And so for a similar reason, the random guessing curve that you would get doesn't really look like a diagonal anymore either. The random guessing curve, you can imagine, in this case, would basically, I actually, no, in this case, the random guessing curve would basically be decreasing from that 1.0 to that prevalence number there. The one that's actually sort of interesting to think about, though, is sort of your worst possible model, right? If you had a model that predicted all your negatives first on top of all your positives, then you could imagine that as you're going down through the threshold, all you're doing is your precision remains at 0 and your recall remains at 0. And then once you start hitting your positive examples at the bottom, then your precision and recall will gradually increase to your prevalence rate at the end here. Okay. Any questions about ROC curves, precision recall curves? The thresholds? Yeah. So it's a little bit unintuitive. You can't really do this one-to-one mapping of thresholds to positions on the graph. It's sort of like for each threshold, that's giving you 1 point on this curve, right? And so, for example, for that case where I was telling you about the worst case, where all your negatives are above all your positives, right? A bunch of thresholds will give you the same precision recall. It'll give you 0 precision, because you're getting, if all your negatives are on top as you're going through, you're not getting any positives, and 0 recall. So a bunch of the thresholds would just fall here, if that makes sense, right? And then gradually it would increase. And so what you can do is you can sort of plot out where your threshold points would fall each, but it wouldn't sort of be a nice like line or something like that you would get. And it's sort of a similar, for similar reasons, you would also not see the same thing on the ROC curve. You just don't get that nice mapping there. So you shouldn't make that assumption that your thresholds are nicely mapping to the line of these curves. Any further questions? Oh, okay. So far, we've been mostly talking about all these metrics in terms of like the rankings of them. I sort of mentioned early on that the exact location of the threshold doesn't matter and that the absolute positions of your points don't matter. However, you can sort of think that there are cases where this would matter. You can imagine these two models here that are scoring the same data set. And the ordering of the two are sort of the same. However, I want you guys to think for a second and tell me which one of these two models you think is better. And then I'll get a show of hands for that. Okay, I'll give you 10 seconds. Okay, who thinks that model A is better? Who thinks that model B is better? Okay, you guys clearly got this. Intuitively, you can sort of say, okay, model B is better because it's sort of splitting out the positives and the negatives. It's more confident about its positive predictions and its negative predictions, versus here they're more evenly spaced out. And for all the point metrics we've been looking at, it doesn't matter what those exact locations are, because all that matters is the relative ordering. And so this has sort of motivated the creation of another loss function called the log loss function, which is much more values these confidence predictions. Right? So that first one, right, that first point is just recapping what I just said previously. And so one way to think about this, I'm just going to bring this down. I guess that one's there. I'll bring it back in a bit, is you have this gain term here that we're talking about, okay? And so you have your probability Px that your model, that's like your predicted model output, Px. And then you have y, which is true label, right? Which is the actual label. Right? And you can sort of think of gain as imagining you have a betting machine. Okay? You have your algorithm is getting these examples, and it's placing a bet between 0 and 1. as to if it thinks it's a positive or not. Okay? So say you get examples x1, x2, x3, right? And for the first one in your machine, bet, I think I'm going to bet 75 cents on this guy. This one I'm only going to bet 40 cents. And this one I'm going to bet a whole dollar. I'm going to bet everything on it, okay? And then what you can do, so this is your sort of your P of X. And then what happens is you look at the true labels and say it's like 1, 0, 1, right? And what happens is if it is correct, then you're just getting the amount you bet. So your gain is 0.75 in this case. And then if it's false, what you get is 1 minus the amount you bet. So in this case, it would be 0.60. And then in this case, since you got it correct, you get a full dollar. Right? And so this sort of makes sense. You want to sort of maximize the gain you're getting. However, if you just do that, then you end up back at this sort of like score-independent sort of regime. And really what you want to do is you want to really reward confidence in your good answers and sort of also, on the flip side, really penalize your bad answers. Okay? And how log loss does that is it basically takes the geometric mean of your gains. And so to write that one down, it's on the other board too, but I'll just write it here to be clear. It's just the product of your xi's, right, to the 1 over n, right? And so the reason why this is really penalized is, if you have confidence, it's right, you're multiplying them together, but if you get something wrong, like say this guy's true label was 0, right? Then your gain is 0. And it doesn't matter how confident you were with the other ones, right? Your whole geometric mean is just going to go to 0, and it's going to crash you, right? And so it's really strictly penalizing if you're confident and you're wrong. So you better be sure when you're confident. And this tends to produce well-calibrated models, which is sort of something that we're exploring in problem set 2. And so you can sort of see why you would really want to make sure that you're confident only in the predictions that you're actually confident about. And this kind of log loss is basically gaining a lot of popularity for these reasons in Kaggle. Any questions about log loss? Yep.
I guess in the analogy to betting, it kind of seems like that your gain is defined by 1 minus whatever you bet. So like for x2, your gain would be 0.6. Seems counterintuitive. Like if that meant that you only had a 40% chance of it being a positive, why wouldn't you have bet nothing? I guess.
Why wouldn't you bet nothing?
Why would you have not bet nothing? Why would you bet 40 cents?
It's basically you could see doing it that way, right? If you're that's sort of okay. The question is why, if you think that's going to be a 40% chance of an example being positive, why don't you just bet 0, right? Why is that not optimal? And it sort of depends on what you're trying to optimize again, right? So I was talking about accuracy and things like that beforehand, and from an accuracy standpoint, right, it doesn't really matter the exact amount you're betting, right? All that matters is like whether you got it right or not, right? And so from that standpoint, it really wouldn't matter if you're betting 0 versus betting 0.4 or something like that. But what people are oftentimes interested in is they don't want their model to just predict 0 if they think it's 0. They want it to predict sort of a probability of it. They basically would like a confidence score associated with whatever they're predicting. And if you just use that like sort of accuracy representation, you're not going to end up with well-calibrated models that actually output probabilities. It's basically not incentivized to do that. Versus for the log loss case, right? You sort of it's much more incentivized to predict according to what it actually thinks its confidence in that score might be.
Yeah, so just betting 0 would be going back and reverting to the model.
Yeah, exactly. Okay, and yeah, so that basically covers log loss. Any further questions? Okay. So that sort of brings us to a close on our different summary metrics. So just to recap, we went over these confusion matrices, and then we talked about various point metrics which depend on specific thresholds, And then we talked more about these summary metrics, AUROC and AUPRC, and then finally log loss, which cares a little bit more about creating these well-calibrated models. Let's talk about class imbalance. All right. So if you'll recall, well, let me just shift this up now so that you guys can see what's back here. You have prevalence, right, which is sort of the amount of positives, is your positive-negative ratio. It's the number of positives you have divided by the total number of examples. And generally, people will call a problem heavily class imbalanced if you have like a prevalence rate of less than 5%. I mean, anything other than 50% is class imbalanced, but it sort of becomes worse and worse as you have more and more imbalance. And the problem is, as you get these imbalances, a lot of your metrics become a lot less meaningful. And, for example, when you're learning, if you have a heavy imbalance, your learning function might just optimize solely the majority class and completely ignore the minority class. And you oftentimes see these kind of problems in like retrieval scenarios where you've got this large set of examples and you're like a search page, for example, and you want to pick out just the right ones. Right? You have millions of pages you could return, and there's only a very small fraction of those that might be correct. Right? And for the search engine case, right, you want to sort of optimize, you want to sort of fix your precision. So you're like, I have to be at least this precise, and then you try and optimize your recall so that like as many pages of results as possible are correct. And then on the flip side, for like a medical test, you sort of really want to not miss any disease conditions, and then you're trying to optimize your precision, so reduce the number of false positives you might get. So to talk about specific metrics and how they get affected by these various imbalances, right? You could have, if you had like a 9-to-1 negative to positive imbalance, so 90% of your examples are negative, right? For accuracy, you could just predict all negative, right? And that would get you a 90% accuracy, which would be a very misleading figure because you're just doing the simplest thing and predicting the majority class. Similarly, for log loss, right? If you have a significant bias one way or the other, say like you have a 90% negative and 10% positive, then you'd basically be incentivized to predict 0.1 all the time, and that would still get you a fairly high loss or a fairly low loss. And then for concepts like AUROC and AUPRC, that's a little bit harder to see, but you can sort of think for AUROC, right? You'll recall that the definition is if you pick a random negative and a random positive, what is the chance that that positive will outrank that negative? And so you could imagine this pathological case where you have your like score line here, right? And say 10% of your negatives are up here. So you've got 10% negatives, right? And then you have all your positives, right? And then you have your remaining negatives all down here, right? So this is like 80%, right? And this is your 10%. This is basically 1 out of 10 are prevalence. Right? And this is kind of a useless classifier. Like in the search results case, that would mean that all your top results would be garbage, right? But then if you look at it from the ROC case, right, if you pick a random positive, right, they're all in here, so they're all within this range, and you pick a random negative, what is the probability that the positive outranks the negative? Well, it's basically, the probability there is basically 1 out of 9, right? Because like any given positive will outrank this 80%, but then this 10% here will outrank it. So it's since you have 90% negatives, only 1 out of those 10% out of those 90% will outrank the positives, right? And so that's a 1 out of 9 sort of error rate in this case. And so then your AUROC in this case, ROC would instead be 8 over 9, which is like 89, about like 89%. Or, well, 0.89, right? Right? And so this also looks really good, even though your sort of classifier is sort of producing something that is not very useful. And so AUPRC sort of gets over a lot of these issues. And the reasoning for why that is that if you'll recall, right, again, writing out precision, right, it's true positives over true positives plus false positives. And recall is true positives over true positives plus false negatives, right? And both of these terms are mainly focusing, right? The numerator is all about the true positives, right? And so it's sort of putting a lot of emphasis, if you'll recall, on that confusion matrix on that top left corner, which is sort of emphasizing the true positives. Versus when you're looking at the other case, where you're looking at specificity and sensitivity, only one of the two terms has true positives factored in. And then the other one is putting a lot of weight on the true negatives, right? So if you'll recall, specificity, right, is true negatives over true negatives. I always forget this one, geez. Over false positives. Yeah. And so this one here puts a lot of emphasis on true negatives. But since you have so many true negatives, it's very easy to boost this number up and therefore get like a misleading sort of AUROC metric number. Any questions on this so far? Okay, and so just to summarize, right, accuracy, it's pretty easy to get a high accuracy in a bad case, in an imbalanced case by just predicting the majority class. You can also design setups. I mean, it's a little bit harder, but you can design setups where AUROC is a very misleading number as well. And then AUPRC still has some issues, right? There's still, like, the imbalance can still throw off your numbers, but by focusing more on the true positives, you're able to at least somewhat account for that. Okay. So that sort of brings a close to our discussion of class imbalance. Let's very briefly go into multi-class stuff. Okay. So I sort of briefly alluded to the fact that in a multi-class case, your confusion matrix is actually going to become n by n, right? Because each row, you have one row and one column per class that you're predicting. And you still want the diagonals. The diagonals correspond to correctly predicting the right class, but then the off-diagonals are going to be sort of confusing certain classes with other classes. And so you can still, at a high level, use a confusion matrix, and oftentimes you can like color it, so from like blue for being very low values to red to being high values, to get an overall impression for how you're doing on this classification problem. And most metrics, generally, instead of considering like a many versus many thing, what they'll do is they'll take one class and then consider all the other classes as the other class and pretend that's a binary classification problem and then analyze them with respect to those performance numbers. Another issue with multi-class stuff is that the more classes you have, the more chances you have for class imbalance. Like there's just more examples, so you can oftentimes have much higher variance in the number of examples you have per class. And so you oftentimes will have a lot more class imbalance there, and you'll have to use basically the techniques that I discussed on the previous section to deal with that. Though another way to help you deal with it is basically this cost-sensitive learning technique. It basically means you just weight your examples based on how common they are. If you don't have many examples of a certain class, then you can basically weight them based on the ratio. So like in this case here, if you had 1 out of 10, right, prevalence, then you just weight your positives by a factor of 10. And so then the overall weight that positives versus negatives are providing to your models is sort of even. Yeah, and so that example there was binary for binary imbalance, but it also works for multi-class imbalance. And I believe that's really it for this slides today. So yeah, that basically covers everything. Thank you for coming today. Are there any last questions about this stuff before we break? Yep.
I have one more question about sampling.
Sure. Oh, okay. So the question is, why is your monetary gain defined as like either you get the amount you bet or you get 1 minus the amount you bet? And it's really just a simplification. Like, you could also formulate it in the way that you were talking about. It's just a simplification that we make in the binary class case, where essentially, like, your probability of it being one class is 1 minus the probability of it being the other class, right? For the multi-class case, you couldn't really get away with that, and so then you'd actually have to formulate it in the way that you're talking about. Yeah. Any more questions? Okay, well, great. Thanks for coming. See you guys on Monday.